Welcome. Today I'm going to tell you how to read bond line structures in organic chemistry. You can think of bond line structures as adaptations of Lewis structures. Bond line structures do not show any carbon or hydrogen atoms when they're connected together. However, hydrogens might be shown when they're connected to other atoms, such as oxygen. This is an example of a bond line formula, sometimes also known as a Kekule structure. Now, the way you read this is that the lines here indicate bonds, and because we only have single lines here, this is all single bonds. And so you would read this as CH3 at the end, so you have a carbon attached to 3 hydrogens at the end, and that goes the same for the other side. And then in the middle, with this little bend, you have a CH2. So that means that in the middle you have a carbon attached to 2 hydrogens. The Lewis structure for this would be that you have the carbon attached to 3 hydrogens at the end, and then you go up here and you have a carbon attached to 2 hydrogens, and then you have your last carbon attached to 3 hydrogens. As you can see, each line in our bond line formula indicates a connection between carbon atoms. Because the structure down here is very messy to read, we like to keep it nice and simple and simply write this, which indicates that we have 3 carbons and then 3 plus 3 plus 2, which is going to be 8 hydrogens. For this, we can tell that the tips ending in single bonds are going to be CH3s, and that corners with single bonds are going to indicate CH2s. How many carbons and how many hydrogens would you say are in this molecule? We can start with the ends. We know that these ends are ending in single bonds, therefore these ends should end in CH3s. The middle parts, these corners, are CH2s, and therefore if you count them up, we have 4 carbons, and then for hydrogens, we have 3 plus 2 plus 2 plus 3, which is going to be 10 hydrogens. In this example, we have a double bond, indicated by the 2 lines here. So these 2 lines are both connecting carbons at the end, so there's a carbon here and there's a carbon here. Okay, and those carbons are connected via a double bond. This green carbon and this blue carbon are connected via a single bond. So if we wanted to find how many carbons and how many hydrogens we had, we already know that we have 3 carbons. Now let's try to find a number of hydrogens. Now at this end here, we have a CH3 because it ends in a single bond. Now let's take a look at the middle. This carbon is attached to 1, 2, and 3 bonds. 2 from the double and 1 from the single. And so that leaves only 1 more place for a hydrogen to go. As we recall the octet rule, right? Carbon cannot make more than 4 connections. 2 connections are already taken up to connect it to the green carbon. 1 connection is already taken up to attach it to the blue carbon. Then we have 1 more connection left, and that will be used to connect to the hydrogen. When carbon has no lone pairs, what you can do is say, I know there are 4 places available. Now I'm going to subtract what is already being used. So in this case, what's already being used is these 3 bonds. And so that will give you the number of bonds that are left for carbon to make, and that'll be your number of hydrogens, as the CH bond is a single bond. Now let's use that strategy again to find how many hydrogens are attached to this carbon over here with the double bond. So this carbon has 4 places available. It has 2 bonds from this double bond already taken up, and so that leaves us with 2 bonds left, which are going to be taken up by 2 hydrogens. So at the end here, we're going to have a CH2 instead of a CH3 because this end right here is a double bond. Now we can add up our hydrogens. We have 2 plus 1 plus 3. And so that's going to be 6 hydrogens. Now here's another example, and in this case we have a triple bond indicated by these 3 lines here. So these 3 lines connect a carbon over here and another carbon to the right. Okay, and at the end here we know that it ends in CH3 because we talked about how if it ends in a single bond, it's a CH3. Now let's figure out how many hydrogens we have over here that are involved with the carbons connected by a triple bond. We will use a similar strategy as before. So this blue carbon has 4 places available. 3 are taken up by the triple bond. Then 1 more is taken up by the single bond. And this is going to be 0. So this carbon here in blue has no hydrogens because its octet is already filled. Now what about the green carbon? Well, this one has 4 places available and 3 are already taken up by the triple bond. And so that leaves us with 1 place available. And so at the end here, we're going to have 1 place for 1 hydrogen. So at the end, we're going to have a CH. So if you see a triple bond at the end, you always know that's going to be a CH. Now, how many carbons and how many hydrogens in total do we have for this molecule? Now, how would you read this molecule? This one is called benzene, which is often seen in organic chemistry. As you can see, benzene is going to have 6 carbons. Benzene has alternating double bonds. Now, how many hydrogens does benzene have? We can use the same rules from above. This carbon has 4 places available. 2 are already taken up by the double bond, and then another one is also taken up by the single bond up here. And so that leaves us with 1 space available, which means that this carbon here has 1 hydrogen. so we see a CH here. It's the same case for the other carbons as well. This yellow carbon has 4 places available, 2 are taken up by the double bond, and 1 is taken up by the single bond over here. And so that is also going to be 1 more space available, which means this is also a CH. Right, so basically benzene is going to just be a ring of CHs. Now let's find the number of carbons and hydrogens of this molecule here. Immediately looking at this, I see that the tips are going to be CH3s because their ends are single bonds. So at each of these ends, I have a CH3. Now let's dive into the middle part. In the middle part, over here, we have another carbon. And this carbon, well, it has 4 places available, okay? But it already has 3 places taken up, okay, by those 3 single bonds. And so 1 more place is left, therefore it's going to be a carbon attached to a hydrogen, so a CH. There is another carbon here at this bend, and as we said, a bend which is made by 2 single bonds is going to indicate a CH2. And then we have a last carbon over here, and again this carbon has 4 places available, and 4 are already taken up because this carbon in this little center here at that intersection is already attached to 4 bonds, 4 single bonds. It has 1 connection to each of these green carbons and 1 more connection to this yellow carbon over here. Therefore, this blue carbon over here has no hydrogens. It's just going to be 1 carbon. So let's find how many carbons in total we have. We have 1, 2, 3, 4, 5, 6, 7, 8. Now, how many hydrogens are in this molecule? If you add them all up, then you will get 18 hydrogens. Here's another example, and again, we would like to find how many hydrogens and how many carbons exist here. Let's go ahead and fill in what we already know. At this end, we have a CH3 because it ends in a single bond. At this end over here, we have a CH2 because it ends in a double bond. And over here, we have a CH because it ends in a triple bond. And so those are the ends. Now, what about here? This is going to be a carbon, and it is attached to 1, 2, 3, 4 bonds already. Therefore, it's not going to have any room for hydrogens. And so it's going to just be a single carbon. Over here, we have a CH2 because we discussed that bends made of single bonds are going to just be CH2s. If you want to use the strategy for it, you can say that there's a carbon and it is already attached to 1, 2, so that's going to be 4 minus 2 places already taken up, which leaves 2 places available for 2 hydrogens. Finally, we have a carbon here. The carbon would have 4 places available, 3 already taken up by the triple bond over here, and 1 is already taken up by the single bond to its left. And so there are no places for hydrogens. Therefore, again, this is just going to be a single carbon. Now try to find out how many hydrogens and how many carbons we found for this molecule. As you can see, as we go through these examples, the hydrogens are implied when they're connected to carbons. So always from a bond line structure, you're able to tell how many carbons there are, and then we just have to do a little bit of extra work in order to find the implied hydrogens. Here's another example. So at the ends, we can already fill in that we know that they're CH3s, because they end in single bonds. Next, here in the center, we have a CH2, because that's going to be a bend with single bonds only. And then over here, we have a CH, because this hydrogen has 4 places available, but 2 are taken up by the double bond, and then another one is going to be taken up by the single bond, leaving 1 place available for 1 hydrogen. And finally, for our last carbon, it will be the same case. We'll have a CH, because it has 4 places available, but 2 are taken up by the double bond, and then 1 is already taken up by the single bond. Right, and so 1 place is available, which leaves us 1 place for 1 hydrogen. Therefore, we have 5 carbons in total, and we have 10 hydrogens in total. That's the end of this video. There's a link down below if you're interested in science and math tutoring, my website, and my publications. Now, if you're interested in another video to watch, I have one here about Lewis structures, and one here that is my latest video. Thank you so much for watching, and I will see you next time.